Greetings and welcome to section 2.7. Yes, this is a little bit out of order, and my reasoning was if we did this section back in chapter 2, then by the time we got to integration in cylindrical and spherical coordinates, which is chapter 5, you may have forgotten everything. So I figured I would just move this section, which is just a description of these two coordinate systems, move it here, and then in the next section, we'll be integrating using these coordinate systems. The first coordinate system we want to talk about is cylindrical, and that's basically just a combination of polar and rectangular. So the z is the normal z from the Cartesian coordinate system, and r and theta are your polar coordinates from the polar coordinate system. Now, there's going to be a lot of conversion formulas in this section, and I just want you to rest easy that you do not have to memorize all of these conversion equations because I have them all on the last page in a chart which tells you how to go from any one system to another system. And I also have the volume elements, and that will be important when we start integrating, but we won't use that today. And I will give you this on the next test. You don't have to memorize this. Let's do some examples of converting from one system to another. So let's plot in cylindrical coordinates this point and find its rectangular coordinates. And I've already put in the conversion formulas for us from that last page. And so let's do the plotting first. R is 2, theta is 2 pi over 3. So the positive x-axis is theta equals 0. Positive y-axis is theta equals pi over 2. So 2 pi over 3 is going to be over here. All right, so we're going to go to the angle 2 pi over 3. Let me erase some of this stuff. We're going to go to the angle 2 pi over 3. We're going to go 2 units out in that gray plane. And then since z is 1, we're going to go up 1 unit. So we're going to be about there. All right, so it looks like x is going to be negative, y will be positive, and of course z is just z, so z will be 1. So if we compute r cosine of 2 pi over 3, 2 pi over 3 is here. This is an xy plane, so the cosine of 2 pi over 3 is negative 1/2, so we get negative 1. And then sine of 2 pi over 3 is the square root of 3 over 2. So this gives us root 3. So the rectangular coordinates are going to be x, y, z equals negative 1, positive root 3, positive 1. Okay, find a set of cylindrical coordinates for this point with r and theta positive. Now, we always choose r positive for integration, but theta being positive is a choice that your textbook, My Open Math, makes. They want theta positive. So I'll show you how to work with that. So our conversion formulas are here. R is the square root of x squared plus y squared. So that's the square root of 3 squared plus negative 3 all squared. 9 plus 9 is 18, which is 3 root 2. Tangent theta is y over x. So y is negative 3, x is 3. So that tells us that tangent theta is negative 1. So let's look at this point, just looking at the x and the y. X is 3, y is negative 3. So I'm here in quadrant 4. The tangent of theta is negative 1. So that tells me that theta is either negative pi over 4, or since we want theta positive, we're going to go around this way and use 7 pi over 4. So we're going to cross that one out and use 7 pi over 4. And z is z, which is negative 7. So we're going to get 3 root 2, 7 pi over 4, comma, negative 7. Now we're going to go cylindrical again. So same conversion, cylindrical from rectangular. All right, so r is the square root of x squared plus y squared. So that's the square root of 25, which is 5. Tangent theta is y over x, which is 5 over 0, which is undefined. So theta is either going to be pi over 2 or 3 pi over 2. Which is it? Well, let's look at these two coordinates, 0, 5, on an xy plane. x is 0, y is 5 is up here on the positive y-axis. So 3 pi over 2 would be no good because that would be down here, negative y-axis. So we want to use pi over 2. And then z is z, so we're going to get 5 pi over 2, 2. All right, one more. Again, on a test or something, I would give you problems that you didn't need a calculator for, but I took this one from MyOpenMath. They want 2 decimals, and they want r and theta positive. Start here. R is square root of x squared plus y squared. That's 9 plus 1 is 10. And we'll convert that to a decimal in a minute. Tangent theta is y over x, which is negative 1 over 3. So theta, now you're going to need a calculator. I want to show you what to do. Theta is going to be tangent inverse, well, our first theta, negative 1 over negative 1 over 3. And if you do that out on a calculator or Desmos, you get negative 0.3217. So let me show you a picture. I always, to do these, to determine theta, I always make an XY plot of X and Y to figure out what quadrant I'm in. So X is negative 3 and Y is 1. So I'm up here, okay? I'm in quadrant 2 in the XY plane. Now, what this calculation is giving me, tangent inverse always gives an angle between negative pi over 2 and pi over 2. So what's happening is that this is negative 0.3217 in here. But I'm up here, right? So this isn't the correct angle. This, by alternate interior angles, this is 0.3217 here. I want this guy, which is pi take away 0.3217. So I want WANT theta equal to pi minus 0.3217. And I did that out on my calculator, and I got 2.82, which is better because it's positive, A, and B, I know that's in quadrant 2, and then z equals z, which is 5. That's always pretty easy. And so if we finish it up, root 10, I got 3.16 for that. And then our theta is 2.82, and then our z is 5. Okay, so now let's look at some common surfaces in cylindrical coordinates, and these we will be using in the next section to integrate over. So the main surfaces in cylindrical coordinates that are going to come in handy are cones. Cones are going to be r equals any constant times z. So for example, r equals z is a cone, and we're going to get the top of the cone because we want r to be positive. So there's kind of a derivation here. A cylinder is just fixing r. So theta can be anything, so you can go all the way around the circle. Z can be anything, so you can go up and down. So for example, r equals 5 is the cylinder, x squared plus y squared equals 25. And you might say, well, that's a circle. And yes, it is. In R2, that's a circle. But we're in R3, so you take that circle and you extend it up and down because z can be anything. If r is the square root of z, then square both sides and you're going to get an elliptical paraboloid. And then if you just fix theta, you're going to get a half plane. If you're forcing r to be positive, that's why you're only getting the half plane. So let's look at an example. Convert this equation in cylindrical coordinates to an equation in cylindrical coordinates and sketch. Okay, so we can replace, everywhere we see an x squared plus y squared, we can replace it with an r squared. And everywhere we see a y, we replace that with r sine theta. Okay, divide both sides by r, which is fairly safe to do. R equals 6 sine theta. Now in polar coordinates in R2, r theta, we know that this is a circle oriented like that on top of the x-axis, and the diameter is 6. So that's what it looks like in 2D. And so in 3D, you're just going to let z roam. You're going to get a cylinder. Here's the positive y-axis here. So there's my circle, and then I'm just going to extend it up and down. There's my cylinder. Okay, spherical coordinates are a little trickier because they're unfamiliar. They use, well, actually one variable is familiar. Theta is the theta from polar coordinates, but the other two are a little bit unfamiliar. Rho is your distance from the origin, positive distance, And phi is the angle between the positive z-axis and the ray that joins the origin to the point. And so I think going to Math Insight here would be helpful so you can see exactly what's going on. So here I've got a point in space. You can see x, y, and z there. Changing rho is going to change your distance from the origin. So that's all rho does. Changes the distance from the origin. So if you fix rho, you're going to get a sphere because you want all the points a distance from whatever from the origin. Now, theta is theta from polar. So this is theta equals 0, and then theta equals pi over 2, theta equals pi. So theta will swing you around the circle, all right? And the most fascinating one is phi. What does phi do? Phi moves you away from the positive z-axis. So phi equals 0, you're on the positive z-axis. Phi equal pi over 2, you're in the xy plane. And if phi goes to pi, you're on the negative z-axis. Now that's it for phi. You can't go past pi. You cannot go past pi. Phi only goes from 0 to pi. If you want to get over here, you're going to do that by changing your theta. It's very interesting. All right, let's go back and do some conversions. I've already put in the conversion formulas from that last sheet for us. And let's see what happens. So we want to do an easy one first. We're going to go from rectangular to spherical. So this is just plug and play. This is going to be square root of 12. And then the negative 2 squared is 4. So that's the square root of 16, which is 4. All right, tangent theta is y over x. So y is 2 root 3. X is 0. So this is undefined. And so theta could be pi over 2, or it could be 3 pi over 2. So in 2D, let's just see where these point. This is x is 0 and y is 2 root 3. So we're up here on the positive y-axis. So that means we need to take theta equal to pi over 2. And then phi is cosine inverse of z over rho. Now, z is given, negative 2. And rho, we already figured out, is 4. So that's cosine inverse of negative 1/2. And then that would be 2 pi over 3. So since phi is 2 pi over 3, that means I'm going to be, remember, this is phi equals 0. This gray plane is phi equal pi over 2. So I'm going to be down here because phi is 2 pi over 3. So I'm going to be somewhere below the xy plane. All right, so let's put these things together. Rho is 4, theta is pi over 2, and phi is 2 pi over 3. Next one, convert to cylindrical. Okay, so, oh, it's the same point. I see. So here I did it in spherical, and I just want to compare with cylindrical. R is going to be square root of x squared plus y squared, which is going to be square root of 12, which is 2 root 3. Tangent theta is undefined. We already did that above. Same equation. So theta is, we already determined that, pi over 2. And z is z, which is negative 2. So in cylindrical, this is 2 root 3. Let me try and erase that. 2 root 3, pi over 2, negative 2. Okay, next one. Convert from cylindrical to rectangular. So here, there's really no choice to make. You just use these 3 formulas and plug in, which you already did. And so there's no, you don't have to choose any values of theta. You just, there's only, sorry, rectangular coordinates are unique. And so you're only going to get one answer. In this case, it's root 3 over 2. And the whole thing's underneath the square root. Root 3 over 2, and then 1. But I wanted to point out to you what this picture means here. When you specify rho, like rho equals 2, that would be the sphere, the red sphere, rho equals 2. So if rho is 2, you're somewhere on that sphere. When you specify theta, theta equals pi over 4, you're specifying what plane you're on. So if theta is pi over 4, you're somewhere on that yellow plane. Finally, when you specify phi, you're saying this is the angle phi here. So if phi is fixed at pi over 3, you're somewhere on this cone, which is an angle of pi over 3 radians from the positive z-axis. So the intersection of that cone, that plane, and that sphere is this point here, and that's the point that we're describing. Okay, let's do one more. Again, this came from MyOpenMath, and so they want both decimals, which I don't like, as you know, and positive values for theta. Rho is always positive, but theta can be positive or negative. They want positive. We do square root. We get 1 plus 25 plus 25, square root of 51. And that's about, I did this before, 7.14. All right, tangent theta is y over x. So tangent theta is -5. So theta, our first try at theta, is going to be tangent inverse of -5. Plug that into a calculator and you'll get -1.373. But again, we need to look at where we are. Let's look at x and y. X is negative, y is positive. So we're up here. We're in quadrant 2. This value here, this is what tangent inverse of -5 is giving us. This is -1.373. But we want this angle, so we want to use theta equals pi minus 1.373, which is 1.77 to 2 decimals. Okay, and then finally, phi is cosine inverse, and you'll never have to do any modification to your phi because cosine inverse always gives you an angle between 0 and pi, so that's kind of nice. So this is going to be cosine inverse. Z we know is -5. And you have to do these in order, like you have to find rho before you find phi because phi is in the formula. Sorry, rho is in the formula for phi. So what was rho? 7.14. Personally, I would use square root of 51 first so I didn't have any rounding error. Then I'd plug this into my calculator, which I did, and I got 2.35. So this gives us 7.14, 1.77, 2.35. Let's look at some common surfaces in spherical coordinates. So in cylindrical coordinates, a cone is r equals some constant times z. In spherical coordinates, a cone, there's a missing phi here, specifying phi. So for example, phi equals pi over 4, and then I showed you how to get the actual cone. This derivation isn't that important. I don't care if you memorize that, but I do want you to know that when phi is specified, that's a cone. When rho is specified, you're getting a sphere. And that's because rho is distance from the origin. And there I did the two derivations for you. And then rho equals a secant phi is a horizontal plane. And the reason for that is that you multiply both sides of that equation by secant, you get rho cosine phi equals, in this case, 1. But rho cosine phi is exactly what z is. So that's a horizontal plane. So let's do an example. Convert to spherical equations and determine the value of phi where these surfaces meet. So if this were, the next section and we wanted the volume maybe of this upper cap, we would have to know the value of phi on that circle there. And so this is going to be an important skill. Z equal 1 is rho equals secant phi. And the way I got that is I used Z is rho cosine phi. So if Z is 1, that says 1 is rho cosine phi. Solve for rho. Divide both sides by cosine. 1 over cosine is secant. So rho is secant phi. All right, and the next one, this is a circle. Sorry, not a circle, a sphere of radius 2. So that's just rho equals 2. Okay, so where do these surfaces meet? Let's set secant phi equal to 2. All right, so I can't solve that, but I can if I take the reciprocal of both sides. So the reciprocal of secant is cosine. The reciprocal of 2 is a half. Now I can solve that. Cosine phi is a half. That would be pi over 3. So this angle here, from the positive z-axis to this circle here, is pi over 3. And so that's the angle where those two surfaces meet. We'll do some more of this next time when we do integration. And I just wanted to mention on the next page the volume elements that we'll talk about when we integrate. The volume element in rectangular is pretty straightforward. dz, dy, dx, we've already talked about that, and any order is okay. Cylindrical, it's the same as polar with the dz. So for cylindrical, you've got your polar rectangle down here, which has area r, delta theta, and then when you extend it to 3D, you add that delta z. So when you do the volume element in cylindrical, you pick up an extra r just like you do in polar. And then the volume element in spherical coordinates is not at all obvious. You don't just switch dz, dy, dx to d rho, d phi, d theta. You need to add in this extra rho squared sine phi. Yikes. And that is actually because the volume element in spherical coordinates, you're looking at the volume of this shape, and that is rho sine phi delta theta times rho delta phi times delta rho. And so you come up with this. So again, you don't have to memorize that. I'll give you that. And in the next section, we're going to use this stuff to do some integrals.